Well, good evening. Thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Tonight we're going to take a dive into AP, take a look at some practices, some topics, and of course the AP exam. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough to teach concepts easier to learn. And with me tonight is Katie Martinez and Greg Foley. Katie's in her 23rd year of teaching high school math. She's also a T-Cube national instructor for us in San Diego. This year, Katie's teaching a few things: Integrated Math 1, AP Precalculus, Calculus 3, and Linear Algebra. Technology has enabled her students to visualize mathematical relationships and make connections across the curriculum. So Katie, it's great to have you with us.
Thanks for having me. I'm excited to be here.
And Greg is the Morton Professor of Mathematics Education at Ohio University in Athens, Ohio. Beginning in 1986, I was only 6 years old. Greg worked with Frank DeManna and Bert Waits to develop their pre-calculus textbook, the first one to incorporate graphing technology. For the past 3 editions, Greg has been the lead author of their book, Pre-Calculus, Graphical, Numerical, and Algebraic, which is the first and so far only AP Precalculus textbook. So great. Greg, thanks for joining us tonight.
Glad to be here. This should be fun.
All right, Greg, what are we going to do tonight?
So we're already done the welcome and introduction, so we're ticking these off. We're going to give an overview of rational functions, and then we're going to share our teaching tips and invite you to share your teaching tips in the chat. And we're going to talk about equivalent forms of rational functions, which will help us make sense of some of the key concepts. And then we're going to examine some AP Precalculus exam items. And then we'll finish off with talking about resources, TI and AP resources. Maybe have a short Q&A, and then there will be a webinar drawing at the end.
Thanks, Greg. And Katie, what can we expect to be able to do by the end of the webinar?
Tonight, we're hoping you can recognize how AP Precalculus extends beyond a traditional pre-calc course, that you can examine technology-enhanced teaching and learning, and that you can consider AP Precalculus assessment and what it means for your own teaching and your students' learning, and also identify available resources, because there's a lot out there that can help us.
Thanks so much, Katie. So just some reminders for tonight. We're going to use that chat window to send messages. If you have a question for Katie or Greg, feel free to use that chat window, and we'll try to get those questions answered live. If we don't, for any reason, hang tight, because at the end, you'll, I believe, get both Katie and Greg's email address. So if you want to email them your questions, I'm sure they would be ready to answer those questions at a moment's notice. We also are recording this, and you will receive a link to the event certificate of attendance and the documents at the end of the webinar. So without further ado, Greg, please share your screen.
Okay. I will try to get my PowerPoint up here. Okay, so we want to start by sharing our philosophy, which aligns with the AP practices a great deal. So technology is a great way for you to link multiple representations and to give your students an opportunity to see those connections across representations. Bert Waits and Frank DeManna talked about the power of visualization, and the graphing technology, the Nspire and the 84, will help your students to make sense of concepts in ways that they couldn't if they before we had this kind of technology. We emphasize, and the AP course and exam emphasize student thinking and communication. So try to get your students to make their thinking seen and heard. Fluency is used with English language and natural language. You talk about being fluent in English or French or Spanish. We want students to be fluent with mathematics, fluent with the technology, flowing between one representation and another, and to make sense of the ideas. We want to encourage you to engage your students in cross-cutting content and cross-cutting concepts. For example, domain range, invertibility, increasing and decreasing. These apply to rational functions, but they apply to all functions. And to really get the best preparation for calculus is to have your students see how these function concepts connect across the entire curriculum and connect to the real world. And last, not least, we want to elevate and celebrate the AP Precalculus mathematical practices. And here they are. Procedural and symbolic fluency. Students need to have paper and pencil fluency, also fluency with the calculator technology. They need to be able to work with tables and graphs, as well as symbols and verbal representations. And encourage communication. Set up your classroom environment so that you allow students to share their thinking and to communicate, work in groups, to communicate in small groups before they communicate to the entire class. Now, the overview of the topics within rational functions in the AP curriculum, there are sort of 4.5 topics. Rational functions in end behavior, rational functions in zeros, rational functions in vertical asymptotes, rational functions in wholes, and then the equivalent representations that is really applies to both polynomial and rational functions. And all of these are related to the practices. You can see the color coding here. Most AP items really cut across multiple math practices and sometimes cut across multiple content areas. In chat, share with us which of these do your students find trickiest. Some of you may be partway through these topics, or maybe you finished the topics. Katie said she just finished these topics already, but many of you are maybe doing rational functions currently with your students. Which of these do students struggle with? And so share that. And then if you have any teaching tips for really good ways to get students to understand some of these concepts, then share those in the chat as well. So what is a rational function? It's the quotient of polynomials. And that's an important thing for students to realize. And it's sort of analogous to a rational number. A rational function is a quotient of polynomials. A rational number is a quotient of integers. And so, you know, sometimes you represent them in fraction form. Sometimes you carry out the division. And we'll see that as we get into equivalent representations. To get across these concepts, if you look on the right-hand panel here, domain range, continuity, concavity, inflection points, etc., down to end behavior. So end behavior is looking at the behavior of the function as x approaches negative infinity and as x approaches positive infinity. For this basic rational function, a lot of these are simple. The rational functions that we will see tonight, this function is shifted to different positions in the plane, and you look at more complicated situations like a cubic polynomial divided by a quadratic. So I think the rational functions that are considered in the AP curriculum probably extend beyond the kinds of examples that traditionally we would have considered at the pre-calculus level. So our tips, and we can see in chat maybe what can be added to this. Get your students to graph and graph some more. Graph enough rational functions to discover patterns. Use tables in concert with graphs, especially to make sense of limits and asymptotes. Get students to link the multiple representations, verbal, graphical, numerical, algebraic. So again, make their thinking seen and heard. look at all these concepts as you are working on rational functions. And then realize that an exam question might focus on a single concept, but other questions, especially the free response, probably are going to ask about lots of different attributes of rational functions.
So there's different ways of thinking about equivalent forms of rational functions. So just like with our rational numbers, we have improper fractions and proper fractions. So here you can see an example of improper fraction where our numerator is greater than the degree of the denominator. But when we go into improper rational functions, it's not just simply comparing simple numbers, but now we're comparing polynomials and keeping in mind what happens when we divide polynomials, which is one of the things our students have to do in this unit. So here's an example where we have a quadratic divided by a linear function. So in that rational function, our degree in the numerator is larger. So if our students go through that process of long division, they're going to get a quotient that is a linear quotient, x plus 1, and then some remainder there. And so these are leading into our end behavior. Just like if we had divided two quadratics, we would actually get a constant function. And so that would give us our ratio of the leading coefficients as that quotient. So here, when we have the quadratic over divided by the linear factor, we can see we get this slant asymptote whose equation is y equals x plus 1. And this is allowing us to visually see and to make the connections with end behavior. I saw lots of folks putting in comments about their students struggle with end behavior. The more we can give them visually the connection of the rational function with that slant asymptote or with the horizontal asymptote graph, the more they're going to be able to symbolically then give us that limit notation as x increases without bound or as x decreases without bound, and visually see that we are actually approaching that asymptote in a slanted manner or in a horizontal manner. The other way to write equivalent forms of rational expressions is to use factoring. And we can see here that our factors, our quadratics, both factor, and they have a common factor on the numerator and denominator. They also have a couple of uncommon factors. So in this example, if you look at that factored form, if you could put in the chat, if you know the answer, which one of those factors or where would the whole be? And also, where would we have a vertical asymptote? Because that factoring form now is leading us into new features, kind of like the long division was leading us into the slant asymptote. We now have holes and vertical asymptotes apparent here. We also have
showing up in the chat.
Yeah, I'm seeing lots of comments about having a hole at x equals 2, vertical asymptotes at x equals 1. Absolutely. And then we have this remaining factor in the numerator, which is our 0, or would lead to our 0, our x-intercept on the graph.
Okay, so that example that we just looked at leads us into our first AP item. And this one deals with the concept of a hole. And but there's some reasoning and communication here too. So it says, in the xy plane, the graph of a rational function has a hole at x equals to 2. Input values above sufficiently close to that x equals 2 correspond to output values arbitrarily close to a y or a function value of 6. So which of the following could be a definition for f of x? So what are you looking at? If you have a hole, you're expecting to see a common factor across the numerator and denominator. Looks like A has a common factor of x minus 2. B has a common factor of x minus 2. This common factor in C is not where the hole is, but notice the distractor. It's like, okay, there's a 6 here and there's a 6 here. This last one probably would not trip most students up, but it's a choice between A and B. So you're going to have to
people
dig a
give
little bit
answer
deeper.
B as an answer.
Yeah. So if we move to the next slide, let's see. What's going on here? Uh-oh, here we go. I jumped ahead. So the answer is B. If you remove this common factor and realizing that it's going to be equal to 1 for all values not when x is not 2, then as you approach 2, you're approaching a numerator value of 6 and a denominator value of 2 minus 1 or 1. So you're approaching this value of 6. And then you can see what this might look like on the 84. So the function's been put into slot number 7, and we're tracing near 2. If you go to x equals 2, you're actually going to see a blank, y equals blank there. And it would say undefined on the Nspire, but on the 84, it would just give you a blank there. But you can trace very close to that hole. The hole is exaggerated. And so if we can pause for a minute, can you demonstrate this function? Do you have this one available to show what this looks like
Absolutely.
on the 84?
So here is our Zoom decimal window with that same function in there. And if you notice, we can't really see where that hole is located right now. So if we want to zoom out, there's a couple ways of doing it. Greg, did you want to talk through how to zoom out, or would you like to?
So why don't you do a zoom standard first of all?
Sure.
Zoom to 6. So in a zoom standard, you don't have the decimal value. So if you trace to the right just a little bit, you look at the crazy numbers you're getting. You're not getting numbers like 0.1, 0.2, 0.3. But if you go to zoom decimal, you'll get nicer X values on the trace readout. So let's trace along there. We can trace and you can see 0.3, 0.4, and so on. When you get to 1, there's no value. And that's because we have a vertical asymptote at x equals 1. But where the hole occurs, we can't see because it's vertically off the screen. So let's go into Zoom and go to Zoom memory on the right. Can you go down to Zoom set factors? Let's see what factors you've got for zoom out and zoom in. Enter. Let's change those to 2. So the factory default is 4, but I like 2, so you're not zooming out so fast. You're going to zoom by a factor of 2 in both directions. So you're going to get 4 times as much real estate, 4 times as much area if you zoom out. So let's go back to Zoom once more with feeling here and go down to zoom out, zoom choice 3. And we want to go to the center. So yes, just use your cursor, your arrow keys to get it centered at the origin, 0, 0. There, almost there. Okay, now enter to zoom out. And it's going to double the X's and double the Y's. And you've got this gaping hole. Now trace. And let's trace to like 1.9 as you know. Oh, it's at 1.9. Can we get there? You can type 1.9. What if you type 1.999 or something? And we get even closer to that hole at 2. Yeah. So you can get as close as you want. And on the other side, how about 2 point, lots of zeros and a 1? And so even though it looks like there's a gaping hole there, that's an exaggerated hole so the students can see it, but there's actually just a single deleted point at 2, 6. And so the right-hand limit, the left-hand limit, as you approach 2, are going to be that common value of 6. And there's just a deleted point in the graph. If you looked at this on the other calculator, it would look continuous, and you have to trace to find that hole. Now, if you type in 2, you'll get y equals blank, because there is no functional value there.
And this really helps our students solidify this idea of a limit approaching a hole as well. We do get into the left and right hand limits with holes. And so using the technology allows us to visually see that, yes, we are getting really close to that same value as we approach from both the left and the right sides along this curve with some experimentation. And the more students experiment and visualize and check out these different rational functions, the more they become comfortable with that idea and sort of build it on their own.
Okay, let's go back to the PowerPoint here and okay, let me make this full screen if I can. Okay, so if you look here, we really used procedures, multiple representations, and communication and reasoning. We've done it all. And so this is typical. If you embed the mathematical practices in your teaching, I think you'll have much greater retention on the part of the students. You do something in October and you want them to remember that in May. Of course, you're going to review, but if you get them to link representations, I think it's going to stick with them a lot longer. And if you get them to talk through their ideas, it's going to stick with them longer rather than doing just the procedures only. And so this idea of a hole, it's just a single deleted point. The right-hand limit equals the left-hand limit equals the value of the missing point. So there's a missing y value. In the example we just saw, A would be 2, C would be 6. So there's a missing point at 2, 6. Okay, and then
So this leads into a similar type idea here where we're looking at a left and a right hand limit, but this time we're looking at it from a tabular perspective. So bringing in yet another representation for our students. So we just looked at left and right hand limits on a graph using the holes. And so now if you examine that table, and we can look through those answer choices as well, but what do you notice as we approach x equals -5? What do you notice on this table?
And if you looked at it on the calculator, it would look very similar, right?
Right. One thing I noticed is it says undefined in the printed table versus this 84 table is telling us that there's some sort of error happening. So what do you notice about these y values as you read from the left and the right, or top to from bottom to top or top to bottom? What do you notice about those output values? And then the next question would be like, how are they related to our graph? So one thing I see is that from the left side, so if I'm traveling from -5.1 towards -5, I'm seeing that these negative values are becoming even more negative. So really we're headed towards negative infinity here if we kept on going with this pattern. And then on the right-hand side, we are getting very large positive numbers as we're traveling back towards x equals -5. And so here we are definitely seeing that our output values, our y values, are going in opposite directions. In fact, there doesn't seem to be some sort of bounded value there. So this is going to give us a vertical asymptote. For my students, reading tables was very unfamiliar to them. So the more I gave them exposures to tables, the more I give them practice with reading and interpreting tables, the more they were able to connect it back to these key ideas of x-intercepts and holes and vertical asymptotes and things of that sort. So giving them tables are oriented in different ways, both visually, horizontally, and vertically, is also goes back to that fluency idea. So we have these two tables showing the same concept, and I believe they have the same function, and they're demonstrating that. Now we have also another way of demonstrating this, which we'll see in a second as well.
Okay, so there's an example. We've been talking about vertical asymptotes. We've been talking about holes. In each case, the function will be undefined. So here we look at f and g. If you look at the denominator will be 0 when x is 5 in both cases. So, but let's think about the limits as we approach 5 from the left and the right-hand sides. How do you think the table of values of these two functions will compare when we look at them on the technology? And let's go ahead and try to take a look then. So here you see them on the Nspire. And you can have both F and G. So one of the nice things about the Nspire, instead of having Y7 and Y8 or Y1 and Y2, you can actually have F values and G values. So you're using the same letters. Another thing is it says undefined at 5. It doesn't just give you a blank or say error. So it's a little bit nicer on the in the Nspire. But notice that for F, as you get close to 5, coming in from the left through values less than 5, we're getting large negative numbers. Coming in from the right, we're getting large positive numbers. So it's becoming unbounded. And so you'll have a vertical asymptote. But on G, coming in from either side, we're getting closer and closer to 8. It's kind of interesting too, that if you don't pay attention to the decimal point, for example, at 5.001, they look an awful lot alike, right? 8001, but the decimal point makes a huge difference here. In one case, we're approaching 8. In the other case, it's blowing up to positive and negative infinity.
And this really gave, when I gave examples like this with my students, it really gave them the opportunity to explore those limits in a number sense. They have tangible sense of numbers. They know when numbers are coming towards the same value, or when they're going away from each other, or when they're all blowing up to positive infinity, that sort of thing. And so it gave them that ability to compare and contrast. Comparing two different functions that are super similar, but in the table, we can see them numerically either approaching a single value or not, and having those rich discussions with each other about the why, the how, what kind of features do we see? What does it mean numerically when we see that undefined as well? And the fact that in this case, that undefined really means two totally different features on these graphs.
Right.
Still a discontinuity, but an important feature to pick.
Yeah, the side-by-side comparison really helps drive home the point here, I think. Okay, so this next one is...
This next one is from one of the calculator released questions on the AP exam, where we're given a function here, and you can see that we actually have 3 variables in that function. We have C for cost, we have an unknown B value, and then we have our X, which is the number of items being produced. And so in this question, our students are examining a rational function. They're asked to ultimately find the average rate of change, which is a concept, if you recall, that's coming from the start of Unit 1. It's coming from the first half when we first talked about polynomials and the meaning of average rates of change and how the average rates of change and all those concepts that when we talk about cross-cutting these concepts, we're bringing these average rates of change right back into our rational functions. They're not living in their own little silos. So in this problem, our students had to first do a little paperwork here to calculate the value of that constant B. So they had to interpret the problem and use either of essentially the points that were provided to us with the number of items and the cost, and solve for our B algebraically. And then we can define that function. So you can see here, we've defined that function to be the Y8, and you can define it as any of them. And we define the rational function right there in our handheld. And we have all these abilities to recall any variable function that we have defined in our 84, same with our Nspire, and do some calculations on it. So we can see the first line there. It says Y sub 8 of 20 is 65. That's just a verification that we had we have the correct B value. It's a great way of checking that you have the correct B value. If we substitute in the other number of items, we produce the same cost that's provided in the problem. And then we did some calculations. Now here we calculated the 30th, the y8 of 30 and y8 of 40, so that we could do our quotients difference quotient, sorry. So we could do our difference quotient to calculate the average rate of change. Now, had our students not understood that we have coordinate points involved to algebraically solve for B, and that they need to have those skills in order to solve for B first, then they wouldn't have been able to get that difference quotient in there. But with the power of our technology, with using the defined functions within our y equals or within our f of x, or on Nspire, we can define as f of x or g of x. We can recall those functions and have our students do these calculations right there on our home screen, and we don't have to take away from the timeliness or the possibility of getting any errors. Yes, this was that was definitely a calculator question. I saw that pop up in the chat there.
Right. And so, yeah, and they were asking for approximations, which it makes sense in a model. I think most of the modeling questions are going to be calculator active. And this is a little bit different than what you would normally expect in a pre-calculus. I mean, that not only do you find the model, but then you use the model to find a rate of change. And so this is one of those questions where it's asking you multiple things and is testing multiple skills in one item. So this one, the rational function is given here, and it's a cubic over a quadratic. I'm not sure we've seen one of those yet tonight. In the XY plane, which of the following is the slope of a slant asymptote of the graph? So we've got the concept of slope, slant asymptote. How would your kids approach this? So you might put some thoughts in the chat. If this is calculator active, well, they might try drawing a graph. If I draw the graph in the standard window, this is what I get. It looks like it might be incomplete. I think we could probably factor the denominator pretty readily, right, into x times x minus 4. So you expect it to be undefined at 0 and at 4. If you look super carefully, there is a hole at 0 because there's a common factor of x in the numerator and denominator. So there's a hole, and there's probably then a vertical asymptote at 4. There might be more graph. And can you imagine where the slant asymptote would go? And couldn't you tell me what the slope is? Well, you might be able to eliminate 0. It looks like there is a slant to the asymptote. If you had a slope of 0, it wouldn't be a slant asymptote. So A, we can kind of toss away. But this does not look quite like a slope of 1, which might throw students. The scale on the x and y axis will not be the same if you use zoom standard on an 84, because the window itself is not square. The graphic viewpoint is wider than it is tall, and so you get a distorted graph. Okay, now have you had time to think about how you might approach this problem?
Yeah, we had lots of comments about long division. Some folks mentioned factoring. I even saw some comments about just comparing the leading terms.
Okay, so very good. So students might try to jump into algebra, and you could factor your heart out here and simplify it, and then so this is one where maybe we're using both kinds of re-representation, both factoring the numerator and denominator and long division to get in either case you get a quotient polynomial that's linear x plus 3. But those that were in the chat that said, hey, I know that if I divide, I'm dividing x cubed by x squared, so it's going to start off x. It's going to be x plus some constant. I don't need to know that constant 3 to answer the question of what is the slope of the slant asymptote. I only need to know that there's an understood coefficient of 1 in front of the x, and so the correct answer is B.
Yeah, I saw a great suggestion come in from Kim that if they were allowed to graph, and I highly encourage the use of graphing calculators, even for non-graphing problems when you're doing classwork at least, because it does give them that visualization. And Kim said if they could graph this, they could just type in lines with these different slopes to see which line is parallel to this end behavior right here.
Very
And
nice.
instantly see
So,
half of the end behavior.
so if
And
you
what a
typed
great
in y
suggestion.
equals x, you could see that it's pretty much paralleling this, even if you have kind of a crummy graph like this one.
And such a great power visualization right there is
Yeah.
connecting the graphical to this algebraic, and then bringing in the end behavior, because as we said earlier, end behavior is so key to this unit. It is such a difficult concept, and so giving our students that ability to visualize it and explain and communicate in written form, in verbal form, what's happening as we're approaching the ends.
Right. So here's the green, the function graphed in green, and you can see the slant asymptote, which we remember is x plus 3, so slope of 1, and then the vertical asymptote at x equals 4. So this is more of a complete graph. They would have to zoom out a little bit and then use a square window. You could use a double decimal window, and you get close to, I think you get a little piece of this, but I actually sort of shifted a double decimal window to get this image. Okay, so if we were to try to write down all of the cases, and we can do it, this would be what the theorem looks like for end behavior, vertical asymptotes, x-intercepts, and holes. I think the end behavior part is worth taking a quick look at. If the degree of the numerator is less than the degree of the denominator, you have a horizontal asymptote and it's y equals 0. If the degrees are the same, numerator and denominator, then you can look at the quotient of leading coefficients and you'll get a horizontal asymptote. If the degree of the numerator is larger than that of the denominator, then the quotient polynomial will reveal the end behavior asymptote. The vertical asymptotes, x-intercepts, and holes are tricky when you have repeated roots, as we've seen from the examples. So to put these, to say these occur at real zeros of the denominator, provided that the zeros are not also zeros of the numerator of greater or equal multiplicity, that's quite a mouthful. And I think rather than trying to get students to memorize these theorems as rules, I think going through experience and seeing multiple examples is going to really stick with most students. There may be a few students who can do this in your class, but I think the majority of students are better served by doing lots of examples and discovering patterns and making connections rather than trying to memorize. Memorization is not in the spirit of the communication and reasoning. Okay, and then this one, number
Going
26.
back to your
That's
comment
yours,
there,
Katie.
Greg, about those repeated factors, my students, this is probably one of the areas my students struggle with the most, is understanding when we have repeated factors. Does it create a hole? Does it create a vertical asymptote? Like, what is that feature that we're truly looking at? And so here's one of the questions that they may see on the AP exam. We can see we've got a quadratic on the numerator, we have a factored cubic on the denominator. And this is one of those times where our reasoning skills, our interpretation, and how we explain things to each other and to the class is really important, because these are very, very wordy. If we were to narrow this down and look at the factored form of that numerator and compare it to the factored form of the denominator, you want to go
We would
forward a
get something
slide.
like this.
Absolutely. And so we can see we do have some common factors that have now divided out of this rational function. And so now when we examine sort of that quote unquote simplified rational function, we are down to this basic 1 over x plus 1. And so there was a hole. We can see that we have that common factor when x equals 2. And so it was a hole because, and again, it goes into that reasoning and the communication piece, it was a hole because the multiplicity of the negative 1, which is really where we have a vertical asymptote, was greater in the denominator. So the multiplicity, how many times that factor appears. And multiplicity is a term that we saw back in our polynomials, the start of unit 1. We talked about multiplicities when we did our sketches and we looked at polynomial inequalities even. We had to see how the multiplicities affected. And so multiplicities affect our rational function as well. It's one of those concepts that comes in and out of all of our different types of functions. And so the multiplicity there of that x plus 1 is greater on the denominator, so that's leading to our vertical asymptote. My students really have to try a couple of these. They have to experiment around. They have to play around with those exponents and seeing how, if the numerator's exponent is larger, higher multiplicity than the denominator, what kind of feature do you have? We go and we examine them on graphs. We examine them with tables. The more that they get exposure to these, the more they're able to explain their reasoning. And so it is building up some of those patterning skills as well.
The ideal in my mind would be for students to be able to see this final form, the second form inside the blue box there, and know almost immediately that this is just that basic reciprocal function shifted over 1 unit. And then realize that because you have the same multiplicity in numerator and denominator, that just says x can't be equal to 2. So there's a hole there. So can they get to the point where they can picture this function in their mind without using the calculator? If you spend enough time with the calculator, you want to try to build up that internal visualization inside the students' minds. So that's something that you should really strive for and encourage them, because they may not even think, oh wow, I could picture this in my head. Just like I can picture a triangle in geometry, maybe I can picture the shape of a graph in pre-calculus, and visualize internally in that way. Okay, this one is a similar kind of deal, right? Let's just do a quick comparison, that side-by-side comparison idea. Here, the square was in the denominator in the previous example. Now we've moved the squared factor into the numerator. So you have the extra, you have the repeated factor multiplicity 2 in the numerator. So in this one, when you simplify, what would it simplify to? Well, the x minus 1 would go away. The x plus 3, one of those factors would be left in the numerator. So this should be just the line, slope 1, y-intercept 3, but it's going to have 2 holes in it because it's undefined in 2 places. There won't be a vertical asymptote because when you simplify it, you don't have that remaining undefined polynomial in the denominator. And so this is what it graphs as. And when you graph at it, is like, what do you see and what don't you see? Well, we see the line x plus 3, but I don't see any holes. Do you? So if we graph and trace, then we can maybe see something. So this might be a time to pause and get out of the PowerPoint and onto the technology.
Yeah,
Thank you.
so on Nspire, I put the function in. You can see that up here. Here's that function definition that's graphed for us. And what we were just seeing is that we can't see any visible holes. So unlike what we saw on the 84, when we did a zoom decimal window, our proportions are actually set up perfectly here. So we have a nice square window. And even if we did a zoom decimal, we still wouldn't see those gaps. We wouldn't be able to see any visible holes or points of discontinuity in here. Definitely aren't seeing any vertical asymptotes. So if we go and we trace along our graph, we can look down there at the bottom right and we can notice when we get to x equals -3, for example, on that x-axis, that we have an undefined value. So that common factor, the one that had the multiplicity of 2 up in the numerator, is producing a hole for us. We can definitely see it's not a vertical asymptote. This gives us that opportunity to talk about the two left and right ends, or right and left limits approaching that hole, are coming together. There's definitely not a gap. We're not seeing, you know, our left side going to positive infinity and the right side going to negative infinity.
Yeah.
And as we continue to zoom or trace over to 1.
At -3, there's something else going on there, right? Because it's happening on the y-axis. We don't have an x-intercept for this graph. This graph does not touch. I mean, it comes really close to the x-axis, but there is no 0 for this function because of that hole where the 0 would have been.
And so I always have my students talk about what are those features, why do you know those features exist, and then always test it with technology. I always have them put it on their 84, their Nspire handheld, whichever one they have in front of them, and test it out and check and do some tracing or use a table. Give me a justification associated with another representation, because the more that they can communicate those things, even if it's a non-graphing testing question, they really need to practice those skills in class, because the more they practice them, the more solidified they will be for that ultimate AP exam in May.
Okay, and should we go back to the PowerPoint now?
Yeah, let's go back to the PowerPoint.
Okay, let's see here. Share.
And we're going to be switching away from multiple choice for the next little while. And we're going to start to look at, oops, this is the same graph right there. This is on the 84, so you can see the kind of the gap in that 84 screen there. And Greg, if you could project the PowerPoint or start the slideshow on that PowerPoint, make this a little larger.
Okay, there we go.
This is an example of our first FRQ. So there's 4 FRQs. The first 2 FRQs are calculator active. So keep in mind that this is the free response question. We want our students to maximize their points on this. They have the ability to calculate. They've got their reasoning skills. If you notice this free response question, it's got a graph, it's got an algebraic like definition, an analytic definition. That's a rational function here, the g of x. And then it's broken down into essentially 6 questions. So 6.6 questions here. The first 2, or all of part A, or most of part A, is talking about function f, which is our graph. We will be coming back to a part 1. And we're going to kind of focus in here just on the pieces of this FRQ that are dealing solely with that graph that's on the screen. Now, in the directions, they told us that we have 2 specific points. I encourage my students, like we have on here, to label their points if there's information provided in the directions. Highlight it, bring it to their attention, draw it on their scratch paper, that sort of thing. So that's right there in front of them, because these 3 parts to this free response question are only about that graph in front of us. And so hopefully we can quickly just answer them. The first part, A part 2, says find the real zeros. Well, it provided to us in the directions and on the graph. So we have that real 0, x equals 3. And then part C is all about, in this case, invertibility. It might be about something different come to the test date, but there's only a few possible options right now for that last part. And so it's talking about the invertibility and the reasoning. You can see that they're asked to provide a reason here. And then if we go on to G, the part that's about G.
Part about G we'll go to, okay.
Oh, sorry.
That's okay.
So the part of this FRQ that's only about G is all of section B. So here you can see an example where we are taking that rational function for g of x, and they're basically asking us to solve it when that function is equal to negative 5.8. Now we could very easily, if we've got those algebraic skills, solve algebraically, but sometimes we might be given a function that's very difficult to work with. So realizing that we have this technology in front of us, how do we incorporate the technology? How do we bring in our Nspire or our 84 to solve it for us with accuracy? Because we need to be as accurate as we possibly can to maximize our points, and also to show our understanding. And so what you see here is I have a screenshot of our Nspire. We have the rational function graphed for us, and when we're solving an equation, we're looking for intersections. We're looking for where the rational function is intersecting our horizontal line down there at negative 5.8. And so finding that intersection point allows us on either platform to answer this question very quickly without error, as long as we've typed it into the handheld accurately. The second part there, the B part 2, is an end behavior question. And so it goes back to understanding the features of the rational function. And maybe the students didn't need the graph in front of them to answer it, but now we're seeing some new language about end behavior that we haven't seen yet today. And that's talking about as x decreases without bound. So it's really important that as we're teaching these concepts and as we're using our technology to enhance our learning and our instruction, that we are re-emphasizing the vocabulary. So as x decreases without bound, meaning we're headed towards the left on that graph, where are our output values? Where are our function values approaching? We can see from the function itself at the top there that we have a higher degree on the denominator. Hopefully we've done enough experimenting, or we remember that parent reciprocal function, the 1 over x function, but this is just a translated function and technically vertically dilated function of that one, that our ends are both approaching, both the left and the right ends are both approaching 0. And so we have our limit notation now.
Sorry.
Oh, you're good. And so now we can go back and look at that one part that mixes our functions together. So we've got, again, we had that F graph, we had our G equation, and so we will always be asked a composition question. And I realize that compositions actually don't come in until unit 2, because this free response could be about both of those units meshed together. But with the graph that we had there, we knew that the point 6, 3 was lying on the graph of F that was provided to us in the problem. And here what we're asked to do is evaluate the composition. So if we are looking at h of 6, we're going to first evaluate the F function, which was one of the points on our graph. So we got that output value 3. And now graphically and also numerically, we can see that G of 3 gives us an undefined value. We can see it with this 9 divided by 0. We can see it on the graph with the vertical asymptote sitting there at x equals 3. And we're able to answer the question, h of 6 is actually not defined. We can, in class, give explanations for that. We can have our students re-emphasize their knowledge of rational functions using the terminology. So emphasizing our vocabulary, emphasizing the concepts that are being shown while answering these questions and utilizing the visualization of the technology.
I wanted to go back just for a second to reflect on this. This is going to be daunting for a lot of students, but for sure they're going to have a composition question. And usually the composition question includes one function that's defined by a formula and the other function that's defined, in this case, sort of verbally and graphically. So they have to read through the graph is strictly increasing on its domain, and the domain is x greater than 2. And it tells you that for sure these 2 points are there. So that you need to know that it's strictly increasing to get the invertibility question. But having these functions defined in kind of a normal way and in an unusual way, and then having to compose them, they really have to keep their wits about them. So giving them some practice with these, and this I think is kind of the standard free response. Also notice that only the very first question, A part 1, uses both functions. All the other 5 questions are either about F alone or about G alone. So I think taking time not only to give the test, but to actually walk through this with them in a way, something like this, I think is going to be really helpful. It's like they maybe won't get the composition question, but they can get 5 out of 6 parts of this correct on that free response item, and still get a whole lot of credit on the exam. So if they are freaked out by the first question and then just skip it, uh, or they spend so much time on that that they never get to the others, that's going to be detrimental to them. So some test taking strategies together with the communication and being able to deal with functions defined in sort of a weird way, really.
And also thinking about how can we incorporate all of unit 1 together? Because right now we're at the end-ish of unit 1, so polynomials and rationals, and that free response question is a great opportunity. We don't have to know anything about exponentials and logs at this point. We could certainly give them a table of values that represent a polynomial function and a graph or the equation of a rational function, or vice versa, give them a graph of a rational and the equation of a polynomial. We can do some easy compositions. We can talk about the zeros, and we can talk about solving equations, and we can refer to the table and ask questions about the degree and why we know the degree might be, 2 or 3, that sort of thing. So think about how can we incorporate what we're currently working on and mesh our content together.
Okay. So AP Central has some really cool resources, and you should be aware of those. We're running short of time. I would like to maybe answer a question or two. And so know about those, as well as wonderful resources also on education.ti.com. And between those and together with what we provided, and other resources that you might be aware of, getting on Facebook groups, et cetera, hopefully that will help. So we drew from the course exam guide. We drew some things from the textbook that I worked on with Dan Kennedy, Rachel Gorsuch, and Steve Phelps, and also some things from the TI website. So here are our email addresses. If you have questions, are the questions in the chat that were never addressed, or do you have questions now? This would be a great time for that, although we probably need to do our drawing, don't we?
Yeah, so we're going to hand it right back to Mike now.
Thanks, guys. Give me control here. Give me 1 sec. All right, so our webinar drawing winner tonight gets a graphing calculator of their choice, and tonight's winner is Jimmy Powell. So Jimmy, congratulations. We'll be reaching out soon to get some information from you, but start dreaming about which calculator you want to receive. And speak of receiving, to receive a certificate of attendance, click the link in the chat window that's coming up. Also listed will be a link for the documents from tonight. And if for any reason these links aren't working, just hang tight. You'll automatically get a follow-up email, and that follow-up email will contain links to the recording, links to the documents, and links to the certificate as well. And if you're watching this on demand, copy that link into your favorite browser to receive your certificate. If you need to give us a call for any reason, 1-800-TI-CARES works great. And you can also drop us an email at ti-cares@ti.com. We'd love to hear from you. Last but not least, when you leave, you'll automatically get a follow-up survey that will appear in your browser. And that really helps us guide what we're going to do in the future. So we would love to hear your thoughts about what you're looking for in our webinars. Huge thanks to Greg and Katie for everything they put together for tonight. Thanks so much. And we will be looking forward to seeing everyone next week. Have a great night.
Okay. See you, everybody.